Okay, so sorry. So this will be cover up our midterm period. So our learning objectives here is to discuss the hierarchical clustering, to explain the hierarchical clustering, and to explain the model-based clustering. Okay, so going back to number 2 to explain the strengths of hierarchical clustering. Okay. Okay, so how do we define a cluster analysis? When we talk about clustering, it talks about combining of similar objects in based on the other groups. Or there are a group of objects that we also combine with their similarities. So if we talk about cluster analysis in data mining, it's about finding out from the group of objects which are similar to each other in the group. But take note that these are only similar and also those similar to the other groups, but they are different from the objects in the other groups. Okay, so the hierarchical clustering is also part of the cluster analysis, but we talk about hierarchical clustering. This is also a forming of a similar objects from the other groups, but this hierarchical clustering produces a set of nested clusters that organize as a hierarchical tree. So an example of the hierarchical clustering is the Dentogram, which composed of a tree-like diagram that records all the sequences of the merges or the splits of the object. So on the Dentogram, as you can see here, these are it composed of one cluster. So in one cluster, there are also two clusters with the similar objects, and under the other, and from this cluster, they are also grouping into similar objects with this. Okay, and this is the dendrogram. So the nested clusters are this one, which also grouping or combining similar objects under from other similar objects from the different other groups. So what are the strengths of hierarchical clustering? Please take note that the hierarchical clustering has no assumption on the number of clusters, because you can also combine clusters or clustering any desired number of clusters that you should obtain by means of cutting the dendrogram or the proper level. So it means that in the hierarchical clustering, there will be no assumption of how many clusters that you have, for as long as you're going to cut the dendrogram based on the proper level of grouping of similar objects. And take note that hierarchical clusterings also correspond to minimum taxonomies. Or when we say taxonomies, it talks about the group of the subgroups of a one group. Example in biological science. Okay, so we have also the example of the biological sciences. We have the phylogenetic reconstruction, and even on the website, we have the product catalogs as part of the taxonomies. When it comes to computer base. So hierarchical clustering has the following types. Okay, we have the agglomerative and divisive. So the agglomerative, this is also a hierarchical clustering that starts with the points as individual clusters, and for each step, they can merge the closest pair of clusters which are similar until they only combine into a one cluster. While the divisive, it starts with one, and then all are inclusive clusters. And at each step, we can split the clusters into each cluster that contains a particular point. So the divisive is splitting a cluster, while the agglomerative, it merging the closest pair of the clusters into a one. So another is the traditional hierarchical algorithms is also used for the similarity or distance of the matrix. So it will depending, it can be merged or split one cluster at the same time or simultaneously. So what are the complexity of hierarchical clustering? So the complexity is about the distance matrix. The distance matrix is used to decide which clusters are going to merge or split, and at least quadratic in the number of data points, and not usable for large data sets. Okay, so the agglomerative clustering algorithm, so since we talk about merging of clusters, so this is the most popular hierarchical clustering technique. So we have the basic algorithm that the procedure is to compute the distance matrix between the input data points and let each data point to be a cluster, and we're going to repeat again, and then merge the two closest clusters, update the distance mix, and until only a single cluster remains. So for the key operation is the computation of the distance between clusters that we're going to merge it from the part distance to make it closest. So different definitions of the distance between clusters can lead into different algorithms. So look at the example here. We have the input initial setting of the clusters. So we can start with the clusters of individual points and also a distance or proximity matrix. So these are the following points, and this is the distance, okay, of matrix that we use to use the algorithm. So after some merging steps, we have some clusters. So we have some clusters. This is the procedure, the first one. And then we have also now the clusters, as you can see. Okay, so these are the following points. And these green are the clusters. Okay, these one are also clusters. And these are the following points. And this is in the intermediate state that after merging the steps, we have the clusters. And after that, we merge the two closest clusters, which is cluster 2 and cluster 5. And also to update the distance. So this is the updating distance, okay, between the cluster 2 and cluster 5. So from this one and this and cluster 3 and 4 are still divided, but this one are totally merged. Okay, the same, combining. And after the merging, as you can see, how do we update the distance matrix? So this is the the cluster 2 and the cluster 5. So they have now connected as merge. But there's also a following question marks for the following points that can be also going to combine other objects from different groups. But for the agglomerative, we combine the different groups as similar objects in the different groups as one. So what is the distance between two clusters? So please take note that each cluster has a set of points. And how do we define the distance between two sets of points? So there are a lot of alternatives, and this is not an easy task to compute for the distance between two clusters. So the distance between two clusters, we have the single link distance. This is the between clusters I and J, is the minimum distance between any object in the cluster I and any object in the cluster J. So the distance is defined by the two most similar objects, okay, as these are the formulas of merging. Okay, so this is the example of the single link clustering. So now let us determine by one pair of points, okay, one by link in the proximity graph. So this is the graph, okay, in the following points, and this is the dendrogram. So if you put in the single cluster example, this is the dendrogram and the nested. So the single link clusters, as you can see, based on the nested clusters, these are the cluster 1, which the similar object of 3 to 6, okay? And the cluster 2, you have 5 and 2. And the cluster 3, okay, this is the combination of the cluster 2 and 1 because of these two similar objects. In the cluster 4, of course, it's the combination of cluster 3, 1, 2, and 3 because of the similar object. And then the cluster 5 is the outside, okay, as the single link. And even in the dendrogram, it's just the same. So in the dendrogram, we have the one cluster here that it was merged with the other clusters that we combine similar objects in the different groups. Okay, so what are the strengths of the single link cluster? So we have the following original points, and this is the two clusters. So the strengths of the single link clusters, they can handle a non-elliptical shape. So as you can see, in the original points, they have same colors, but in the two clusters, the colors have become different. Okay, but this can be clustered based on the similar objects, even in the other groups. And this is also, and again, there's a again the distance. So there's also a limitation on the single link clustering. So the single link clustering is sensitive to the noise and outliers, and it produces long elongated clusters. So this is the limitation. As you can see, they have similar clusters, but when it comes to the color of the two clusters, it is elongated, and that it can be confusing for combining the similar objects. And of course, the distance between two clusters. Okay, so we have the complete link distance between the cluster I and cluster J is the maximum distance between any object in cluster I and any object in cluster J. So that is the another type of distance. The first is single link, and this now is a complete link distance. So the distance in the complete link defined by the two most dissimilar objects. The first one is the similar. This one is dissimilar or really different. So look at here another example again for the complete link clustering. This the distance between cluster is determined by the two most distant points in the different clusters. Okay, and also we have also the complete link. An example of example. So in the nested clusters, that there's a difference because they are also dissimilar objects. So in the cluster 1, okay, the object 4, 3, and 6 are combined. In the cluster 2, okay, are dissimilar, but in the cluster 3, because they are similar, so they are combined into one cluster, and even in cluster 5 as the whole. Okay, but if you go into the strengths of the complete link clustering, these the original points and the two clusters, these are more balanced clusters with equal diameter and less susceptible to the noise. But the limitations of the complete link clustering, okay, that tends to break large clusters. Yes, because this one, it tends to break the large clusters, and all clusters tend to have the same diameter. So it becomes small on the part, and clusters are merged with the larger ones, just like the red dots here. Another is the group average distance. Between clusters I and cluster J is the average distance between any object in the cluster I and any object in cluster J. So this is also the formula. So look at the example here, the average link clustering. Okay, the proximity of two clusters is the average of the pairwise proximity between points in the two clusters. If you use the average link, okay, so this is the nested clusters. As you can see, in the cluster 1, the objects are combined in the object 4, 3, 6. In the cluster 2, okay, you have 5, 2. In the cluster 3, observes the combined points of 2 dots. And the cluster 4 are the combination of cluster 1, 2, 3, and 4, and cluster 5 as the whole. Even in the Dentogram also, okay? So the average link clustering, it compromises between single and complete link. The strength of the average link clustering is less susceptible to noise and outliers, but the limitation, there could be a bias towards the globular clusters. And also we have also the centroid distance, okay, between the clusters I and cluster J is the distance between the centroid R, the centroid R of the cluster I and the centroid R of the cluster J. Okay, so that's the formula. Okay, so the word distance, this is also between clusters I and J, is the difference between the total within the cluster sum of squares of two clusters separately and within the cluster sum of the squares resulting from merging of the two clusters in cluster I and J. So this will be the centroid, okay, based on the formula. So the Ri is the centroid of cluster I, the Rj is the centroid of cluster J, and the Rij is the centroid of Ij. So the word distance of clusters, this is similar to group average and centroid distance, less susceptible to noise and outliers, and also biased towards the global clusters. And also this hierarchical analog of the k-means, that it can be used to initialize, of course, the k-means. So look at the hierarchical clustering comparison between the minimum and the maximum, the Ward's method, and the group average. So there is a differences when it comes to the clustering. So in the minimum link, of course, this is the merging of the similarities of the objects. In the maximum, there are some to be going to split. In the group average, partly merge and partly split. And in the Ward's method, of course, there are most objects are combined, but only few are split because of the larger groups. Okay, and the hierarchical clustering on the time and space requirements for the data set of X consisting of the endpoints. So on the space, it requires storing the distance matrix and also the time in the most of the cases. So there are the steps, and each step, the size of the distance matrix must be updated and searched. Completely can be reduced to O, or the log at the time of more approaches by using appropriate data structure. So it talks about logarithmic functions. And of course, those are the agglomerative clustering. And now, okay, the second type is the divisive hierarchical clustering. So we are going to split the clusters into different groups, as long as for each splitting of clusters, they are similar objects. So it will start with a single cluster composed of all data points. They are split into the components and continue recursively. And it should be monothetic, divisive methods. It can split clusters using one variable, dimensional, and the polythetic, it could use to make splits on the base of all variables together, and the intercluster distance measure can be used, and it should be computationally intensive, less widely used in or than agglomerative methods. And also the model-based clustering, assume that are generated from the k-probability distribution. So the goal of the model-based clustering is to find the distribution parameters, and the algorithm is the expectation maximization, and also the output is distributing parameters and a sub-assignment of point of clusters. So the model-based clustering, it assumes that the k-probability distributions with parameters and given data to compute for the likelihood, and which is also the log likelihood is maximized. So for every point, need not be generated by a single distribution, but it can be generated by the multiple distribution with sum of the probabilities. And of course, as part of the model base is the EM algorithm, so expectation and maximization step algorithm. So we have to initialize the k distribution parameters. For the expectation step, we should assign points to clusters as a probabilistically. And for the maximization step is to estimate the model parameters that maximize the likelihood for the given assignment of the points. So this is the example of the EM algorithm. So initialize the k clusters and then iterate between two steps. So this expectation step, assign points to clusters, and the maximization steps to estimate the model parameters. What is the difference of expectation? So we have to assign the points of clusters, but in the maximization, we have to estimate those model parameters on the clusters. So that will be our topic for today when it comes to the week 6, which is the cluster analysis.